talk about subsequences, and then we will link the development of subsequences to the concepts of limit superior and limit inferior that we have already introduced before. Okay, so let me begin by defining what a subsequence is. Okay, so consider any sequence xn. A subsequence is basically of the form xnk. So let me write that down. Right, so given a sequence xn, a subsequence of the sequence of the form x and k, where the index n of the sequence of the original sequence is now replaced by the index k for the subsequence, where this nk is a strictly increasing sequence of naturals. Okay, so let me give an example to form this up. Suppose that nk is equal to 2k. So therefore, what is nk? Nk by itself is the increasing sequence of even natural numbers, right? So in that case, you have the subsequence x of 2k indexed by k. So given the original sequence xn, what is the subsequence? This is the subsequence which is basically composed of all of the values taken by the original sequence at all of the even natural number positions. So the elements of the subsequence would be x2, x4, x6, x8, x10, x12 and so on, right? So this is just one example of a subsequence. The point is that uh, the elements of the subsequence are elements of the sequence, however they are taken in the same order. So that is what is imposed by saying that nk is a strictly increasing sequence of naturals. So this nk, which is the strictly increasing sequence of naturals, defines basically the points at which the subsequence samples the original sequence. Alright, so our first result is about convergence, right? Namely that a sequence converges if and only if every subsequence of that sequence converges to the same limit. Okay, now again this is an if and only if statement, but one side of this is pretty trivial, right? If every subsequence of the sequence converges to the same limit, then it follows that the sequence converges, right? Because you know, the entire sequence itself is a subsequence of itself, right? So every subsequence converging implies, well, that the sequence has to converge, right? So this side of the implication is actually fairly straightforward, because any sequence is after all its own subsequence, right? So this part is actually easy. So what we will do is prove this, the opposite side, right? Which is to say that if a sequence converges, then every sequence will in fact converge to the same limit, which is in fact the limit of the original sequence, right? So given a sequence, let's say xn, that converges to x, and a subsequence x and k. Okay, I want to argue that x and k also converges to x. Okay, how do we go about doing this? By the definition of convergence, I know that given epsilon greater than 0, there exists some capital N such that the gap between the elements of the sequence and x must be less than epsilon for all n greater than or equal to, let's say, this threshold capital N. This follows from the fact that xn converges to x. Moreover, since nk is a strictly increasing sequence of naturals, it follows that there exists some number k such that nk is going to be greater than or equal to n for all k greater than or equal to k. So think this through, convince yourself that this is fine. The fact that this is nk itself is an increasing sequence implies that there is going to be some point beyond which the values of nk are going to exceed my original threshold capital N. And if you combine these two, it follows that x nk minus x is in fact less than epsilon for all k greater than or equal to k. Because for all small k greater than or equal to capital K, nk is going to be greater than n. And since all entries of this original sequence are within epsilon of x for positions n greater than capital N, since nk is also going to be greater than capital N, this final condition holds, right? And this, if you look at it, is exactly the same as saying that x and k, as k goes to infinity, tends to x, right? And that completes the proof. Okay, so what we have shown is, so we've defined so far what is a subsequence. A subsequence is basically the elements of the sequence are being sampled along a strictly increasing sequence of natural numbers. That is what a subsequence is. Clearly there are infinitely many subsequences for any given sequence. And the first result we have proved so far is that a sequence converges if and only if every subsequence converges to the same limit. Okay. Now, one thing that I'd like you to basically convince yourself of is that the previous result can also be expressed as follows. Okay, this is the result we wrote in the just in the previous page is in fact equivalent to this result, which looks on the surface slightly more general, because remember here I have not written every subsequence converges to the same limit. All I've said is every subsequence converges, and that's equivalent to the sequence converging. So this is a mild generalization. I leave it for you to prove, right? Ultimately, it all boils down to simply showing that if every subsequence converges to the same limit, then it must be true that that's equivalent to saying that every subsequence converges. So the fact that every subsequence converges implies that those subsequences have to necessarily converge to the same limit. Okay, so I leave that for you. So the moral of the story is that a sequence converges if and only if every subsequence converges. That every subsequence converges to the same limit is a trivial consequence of every subsequence converging. Okay, so I leave that for you to prove. Now, after this, there is one more result that I want to prove, which is the following. Every sequence has a monotone subsequence. Right? So this is actually a fairly important result. the sequence itself obviously need not be monotone, but and the sequence need not even be convergent. Remember, what we are saying is that any sequence has a monotone subsequence. Okay, so the proof is essentially going to follow by construction. Given any arbitrary sequence, we are going to essentially show how one can construct a monotone subsequence of that sequence. Okay, so the first part of the proof is in fact a definition. We say the nth term of the sequence xn is dominant if xn is greater than xm for all m greater than n. Right? So we say the nth term is dominant if it is greater than all the subsequent terms of the sequence. Right? That's just, it's a definition at this point. We are going to call a term, the nth term would be dominant if it exceeds every subsequent term of the sequence. Okay? In that case, the proof is now going to boil down to two special cases, right? Or yeah, two cases. Case one is there are infinitely many dominant terms. Right? And case two is going to be that there are finitely many dominant terms. Right? So we've defined dominant terms. There are only ultimately two possibilities for any given sequence. That sequence actually has infinitely many dominant terms, or that it has finitely many dominant terms. Okay, so if there are infinitely many dominant terms, then it turns out it's trivial that I can now construct an increasing sequence. Sorry, I can now construct a decreasing sequence containing only the dominant terms. Let's say subsequence. Containing only the dominant terms. Right? So after all, if there are infinitely many dominant terms, I can construct a subsequence which contains precisely those dominant terms. Right? And it's not hard for you to convince yourself that this sequence, which is made up of dominant terms, has to be decreasing. Right? Because every dominant term is such that it is actually larger than all the subsequent terms. So the sequence that is made by only including the dominant terms is going to be a decreasing sequence, and therefore that defines a monotonically decreasing subsequence of the original sequence. So if I have infinitely many dominant terms, the construction of a monotone subsequence, specifically a monotone decreasing subsequence, is trivial. I just ride the dominant terms to do so. Right? So now we come to case 2. That is, there are finitely many dominant terms. Okay, so if there are finitely many dominant terms, I will actually now construct a monotone increasing subsequence of the original sequence, and that's going to work as follows. Pick n1 such that n1 is larger than all the dominant terms. Okay, so after all, there's only finitely many dominant terms, so I can always pick my first position for the subsequence n1 such that xn1 is in fact beyond, to the right of all of the dominant terms of the sequence. Okay, now having picked n1, I pick the remaining terms of the sequence inductively. So given nk for k greater than equal to 1, pick nk plus 1 as follows. Right? So having picked the position nk, you pick the position nk plus 1 such that x nk plus 1 should be greater than or equal to x nk. That it is always possible to find such an nk plus 1 follows from the fact that nk is not a dominant position. Right? Because it's not a dominant position, there should be at least one entry of the original sequence to the right of position nk, which where the value of the sequence is greater than or equal to x and k, right? So I pick one such position, I call that nk plus 1, right? And then from nk plus 1, again inductively I can go forward, right? Because nk plus 1 is not a dominant position, there is one other position to the right where the sequence takes a value greater than or equal to that value, and so on. And this inductive procedure results in a monotone increasing subsequence. Right, so let me reiterate, this can be done because nk is not dominant. Right, because we have already passed all the dominant terms of the sequence is why we are able to construct this increasing subsequence. So moral of the story is, if there are infinitely many dominant terms, I can construct a decreasing subsequence. If there are finitely many dominant terms, I can construct an increasing subsequence. In either case, every sequence has a monotone subsequence. Okay, and an important consequence of this result is the following. This is called the Bolzano-Weierstrass theorem. WEI. So the Bolzano-Weierstrass theorem states that every bounded sequence has a convergent subsequence. Okay, so this is actually a very important result. We will often refer to this as BWT, the Bolzano-Weierstrass theorem. Well, the Bolzano-Weierstrass theorem is that every bounded sequence has a convergent subsequence. Now, obviously, every bounded sequence is not necessarily convergent by itself, but every bounded sequence is guaranteed to have a convergent subsequence. And why does this follow? It's actually a trivial consequence, it's a corollary really of the previous result that we have just proved. Since every sequence has a monotone subsequence, it follows that every bounded sequence has a bounded monotone subsequence. Right, and since bounded monotone sequences are necessarily convergent, that subsequence will in fact also be convergent. Right, so this is a trivial corollary, follows from earlier result. Okay, so we have basically proved a more general statement that every sequence has a monotone subsequence to prove the celebrated result that any bounded sequence is guaranteed to have a convergent subsequences. Okay, so I will stop this video here and we will continue our exploration of subsequences in the next.